Hi, everybody, and welcome to the Unit 11 review session where we're going to be talking about acids and bases. The format of your test is going to be 12 multiple choice questions and 5 free response. All right, a couple of things to keep in mind. Please make sure that you know the definitions of acids and bases. All right, we went over the Arrhenius definition and the Bronsted-Lowry definition. Make sure you're comfortable with those. Make sure you know what your strong acids are and what your strong bases are. There are some of those that you do need to memorize. All right. And make sure you understand what we mean by strong. Remember, when we mean strong, we mean it is going to ionize 100%. All right. So that's important to remember as we start dealing with some of these problems that we're going to be looking at. All right. So I'm going to go on ahead and get started. All right. Really important that you guys have your calculators for your test. All right, I'm going to be showing you what to do on a graphing calculator here. Of course, if you have a regular scientific calculator, that should be fine as well, but it does need to be able to do logs for this unit. All right, let's get started with problem number 1. What is the pH of a 4.5 times 10 to the negative 4th molar solution of calcium hydroxide? And calcium hydroxide is a strong base. Now, I was nice to you when I said that in the problem. I don't have to do that on the test. You need to know which bases are your strong bases. So let's first look at what's going to happen when calcium hydroxide breaks up in water. All right, calcium hydroxide is a solid. When it breaks up in water, you don't have to write the state symbols, but I'll just go ahead and do that. You're going to get calcium ions, and you're going to get, for every 1 calcium hydroxide, you're going to get 2 hydroxide ions. All right, that's going to be important to remember. Okay, so as you do this problem, a couple different things going on. So what is the pH of a 4.5 molar solution of calcium hydroxide? Well, that means this is 4.5 times 10 to the negative 4th molar. Well, we're interested in her hydroxide ion concentration, and that's going to be 2 times 4.5 times 10 to the negative 4th. So when we find our hydroxide ion concentration, all right, it's going to be 2 times 4.5 times 10 to the negative 4th molar, all right, which is 9.0 times 10 to the negative 4th molar. All right. Again, with your calculator, hopefully you can see this okay. So you're going to go, 2 times 4.5 second EE negative 4. And that does give you 9 times 10 to the negative 4th. All right. Okay. So great. I've given you the hydroxide ion concentration, but I'm asking for the pH. And that's something you really have to be careful of in this particular unit. All right. Is making sure you're reading closely what you're looking for. Remember that pH, that little p in chemistry means negative log. And when it's an H, it's of the hydrogen ion concentration. Now, you have from this, because it's a base, you have the hydroxide ion concentration. There's a couple things you could do from this. You could use Kw and solve for hydrogen ion and then find the pH. Or I think a little bit faster is I'm going to go ahead and take the negative log of this number, all right, and again in your calculator, negative, so the negative sign, right, not the subtraction, but the negative sign, and then log. Negative log of 9 second E negative 4th. I like to close those parentheses. And that's going to give you what we call the POH. So I'm finding the POH because I took the negative log of the hydroxide ion, and that's about 3.05. All right. Well, 3.05, that's the POH. I don't want the POH, I want the pH. What's really nice is if you recall pH plus POH will always give you the value of 14. So if I go 14 minus 3.05, that is going to give me a pH, and my pH is 10.95. And that is the final answer to my question. Again, you certainly could have used Kw, find the hydrogen ion concentration, and then taken the negative log of that. You should get the same answer. All right, let's take a look at number 2. All right, number 2, what is the pH? So that's what we're looking for. of a 4 molar solution of HX when the Ka is 3.5 times 10 to the negative fourth. All right, HX is going to be kind of a generic acid that I give you all the time because it's not real. I can make up the numbers for it. But HX is going to be a weak acid. I know it's a weak acid because of the Ka. All right, any strong acid, I would actually give you that real strong acid. All right, and when a weak acid, while a strong acid ionizes completely, a weak acid only ionizes a little bit. So you get an equilibrium situation. Hydrogen ion plus your X minus ion. All right, we're going to write a Ka expression for this, just like we did our KEQ. We've got our products in the numerator, which is our hydrogen ion and whatever our negative ion is, over the concentration of that original acid. All right, and now we're going to set up an ice chart. So here we go. I'll just continue using this same equation. So ICE. My initial concentration of HX, I told you in the problem, is 4 molar. My initial of my ions is 0 because I don't have any of them yet. They haven't ionized. Now, what is my change going to be? I'm going to lose some of this HX. It's going to become ion. I don't know what that's going to be, so I'm going to call that X. Okay. Well, because it's a 1 to 1 to 1, this H plus is going to gain some. We're going to call that plus X. Whatever H plus gains, the negative ion X, which we'll call big X here, will also gain. So we'll call that plus X there. Our equilibrium, which is what we need, 4 minus X, and then 0 plus X is just simply X and X. Now, I know my Ka that was given to me in the problem, 3.5 times 10 to the negative fourth, all right, is hydrogen ion at equilibrium, which is X, times negative ion, all right, which is X, so it's going to be X squared over 4 minus X. And if you recall from class, we're going to say, because this is a weak acid, that this X is going to be so small, I'm going to take it out. All right, taking out because it's so small, which is going to leave me with 3.5 times 10 to the negative fourth is equal to X squared over 4. Much easier to solve. All right, and when you go on ahead and do this, we can go ahead and put this into our calculator. So 3.5 second EE negative fourth, all right, times 4. So we're going to get that X squared is equal to 0.0014. We're going to take then the square root of that. And so second, where's my square root button there? 0.0014. And that gives me X being 0.0374. All right, so you've done a whole lot of work here, but you do have to be careful because you actually have not answered any question yet. The question was, what is the pH? Well, what does X tell you? X is 0.0374. X is the hydrogen ion concentration. So I'm going to take the negative log of 0.0374 to find my pH. Again, in my calculator, I'm going to hit the negative sign, and then log, and then 0.0374, and I get a pH of about 1.43. 1.43. And that is my answer. All right. So please make sure, especially on these longer ice problems, that you have actually answered the question. Let's look at number 3. All right, so for number 3, if a 3.7 molar solution of HX, a weak acid, is 2% ionized, what is the pH? 2% ionized just means that 2% of this original acid turned into hydrogen ion. So a percent, remember you take that actual percent, divide it by 100, so 0.02 times 3.7 molar. All right, that's a capital M. Okay, and when I do that, 0.02 times 3.7, that gives me 0.074. All right, and what does that mean? Well, that is the hydrogen ion concentration. So I'm just simply going to do the negative log of that. Okay, and I'm going to go negative log 0.074, close that out, and my pH is 1.13. So nice, easy, short problem for you though. All right, so let's go on ahead and take a look at our next problem. A 6 molar solution of HX has a pH of 4.8. What is the Ka for that acid? Well, I gave you the pH. If you know pH, you can find hydrogen ion. Okay. And again, I want to go over in your calculator how to do this. You're simply just going to second, let me do that so you can see it. So I'll clear it again. So second log the negative of whatever your pH is, which is 4.8. And that's going to give me, all right, 1.58 times 10 to the negative fifth. So 1.58 times 10 to the negative fifth is your hydrogen ion concentration. Okay, again, that's what it looks like on your calculator. Once you knew that, you can solve for Ka. So let's take a look over here. You have HX going into H plus big X minus. You want the Ka expression for that. It is H plus times big X minus over HX. All right. Well, you now know H plus, okay, because you knew the pH. Whatever H plus is, the negative ion is the same. All right. So your Ka is going to be 1.58 times 10 to the negative fifth squared, because again, this and this are equal, H plus and the big X minus is equal, over your original concentration, 6. Now to be good, we can take out the 1.58 times 10 to the negative fifth. It won't make a difference if you don't, but you know it, so you might as well. Once we put all of that into our calculator, you should end up, and you should kind of pause and see if you do too, with about 4.16 times 10, and I'm going to actually do this because I can't read my answer key. Negative fifth times 1.58 second E, negative fifth. And I'm going to divide that by 6 minus 1.58 second E, negative fifth. And I get, yep, that's what I thought, to the negative 11th. And that is your Ka. Kas, remember, do not get labels. All right, so you just leave it at that. Okay, fantastic. So let's move on to our last two questions, which have to do with neutralization reactions. Remember, a neutralization reaction is simply a reaction between an acid and a base. It will always produce an ionic compound, which we call a salt, and water. So a student measured 30 milliliters of sulfuric acid into a beaker and titrated it with a standard 0.5 molar potassium hydroxide. The initial potassium hydroxide reading was 14.5, while the final reading was 35.5 milliliters. What is the concentration of the acid? Any neutralization problems must start out with a balanced equation. So I have sulfuric acid and KOH. So H2SO4 plus KOH. Remember, neutralizations are really just double replacement reactions. The potassium is going to go with the sulfate, K2SO4, because potassium's +1, sulfate's -2. Then water. I tend to write water for neutralizations as HOH. It's just a little easier to balance. Of course, you could write it as H2O. And I have a 2 here and a 2 here, and then I'm balanced. All right, what are we looking for? We're looking for the concentration, so that's going to be molarity of your acid, which is H2SO4. We're going to start with the amount, the volume of your standard, and that's potassium hydroxide. Why is that your standard? Because you know the concentration of it. Now, I've given you lab data here with readings from a burette, just like you did in your lab. So what you're going to do is 35.5, take that final reading, subtract from it your initial reading. All right, and when you do that, you get 21.3 mils. Okay, and that's how much of that potassium hydroxide you have. So I'm going to start out changing that just automatically 2 liters because I know I'm going to be dealing with molarity, and that's of KOH. I'm going to convert from liters to moles using the molarity of KOH. So I have 0.5 moles per 1 liter. That's what that capital M means. I'm now going to do a mole to mole. I want to get rid of my moles of KOH. Remember, this was KOH up here. I want to go to moles of my acid. I'm going to do this through the balanced equation. I have 2 moles of KOH for every 1 mole of sulfuric acid. I'm going to stop there and I'm going to solve. You end up getting about 0.0053 when you take, remember, multiply the numerator, divide it by the denominator, but that's moles. You need it in molarity, and remember, molarity is moles divided by liters. Well, that's okay, because at the beginning, I told you that you had 30 milliliters of sulfuric acid. So I'm going to take those moles, divide it by 0.03 liters, because that is 30 milliliters. And you end up getting, when you put all of that in, 0.0053 divided by 0.03, you end up getting about 0.18 for your molarity. All right. Okay, final problem. Let's take a look at another stoichiometry problem. What volume of 0.55 molar sodium hydroxide is needed to neutralize 22.1 milliliters of a 0.3 molar sulfuric acid solution? This is just like solution stoichiometry we did last semester. There's nothing new here. It's just with the neutralization reaction. So I have NaOH, always starting with my balanced equation, plus H2SO4, double replacement, Na2SO4, plus HOH, my water. I'm going to go ahead and put a 2 and put a 2, and now I'm balanced. Now the key to this problem is starting with your amount. Remember, an amount is going to be either in milliliters or it's going to be in grams. It's going to be a volume or a mass. And in this unit, it's going to be a volume. So I'm starting with 0.0221 liters of H2SO4. I am looking for liters of NaOH. I am going to use my molarity of H2SO4, which is 0.33, which means I have 0.33 moles of H2SO4 over 1 liter. That's what that capital M means. I'm going to now do a mole to mole based on my balanced equation. H2SO4 going on the bottom, what I'm looking for, NaOH going on the top. 2 in front of NaOH, 1 in front of H2SO4. My final step, is using this 0.55 molar sodium hydroxide. All right, but I'm going to flip it upside down because I want to get rid of moles of NaOH, and I want to go to liters of NaOH. So this is going to be 0.55. As long as that 0.55 stays with the word mole, you're good to go, per 1 liter, all right, or 1 liter over. Then I'm going to multiply everything in the numerator, divide it by the denominator, and you're going to get a final answer of, let's just double check, just in case my key is old. So 0.0221 times 0.33 times 2 divided by 0.55, and you do get about 0.02, let's say 6, or 0.027, I guess, liters of NaOH. All right. Okay. Well, everybody, good luck on your test. Have a great one.